Have you ever wondered how a service like Google or Netflix can find one specific thing out of trillions of possibilities and do it in like a split second? Well, it's not magic, it's engineering. And today we're going to sketch out the blueprint, the three fundamental pillars that make almost all modern data storage actually work. But let's start at the very beginning with a really basic question. I mean, we all use files and folders, right? It's simple, it makes sense. So why on earth did we build these ridiculously complicated database systems on top of that? Why not just, throw everything into a bunch of text files? Well, it turns out that simple approach hits a brick wall, and it hits it hard. You run into three massive problems. First, your storage just bloats up. It's super inefficient. Second, trying to find anything is a total nightmare. You have to scan everything, every single time. And third, if you want to change just one tiny thing, you might have to rewrite the entire file. At any kind of scale, that's just a complete disaster. And that gets us to the most basic way of storing data, something called a heap file. The name says it all. It's just a giant, disorganized heap of your data. To find what you're looking for, you literally have no other choice but to start at the beginning and check every single record until you get lucky. It's brutally slow, and that's the core problem we need to solve. So, how do we start to fix this mess? Well, our first pillar, our first big idea, is ordering. It's all about taking that chaos and deliberately imposing some kind of structure. This one simple change takes us from brute force searching to something way more precise. And you can see the before and after right here. On the left, you've got that heap file, where you're stuck reading everything. But on the right, you have an ordered table. By sorting the records by some kind of key, think of it like how a dictionary is alphabetized, we can now jump directly to the section we need. It's the difference between reading an entire encyclopedia to find one fact versus just using the index. And this is where ordering gets its superpower. It unlocks incredibly powerful operations, like a range scan. Let's say you want to find all your emails from last Tuesday. In an ordered system, it's easy. The database just jumps to the start of that day and reads forward until it hits Wednesday. But in that old, unordered system, it would have to look at every single email you've ever received. The performance gain here is just astronomical. Okay, so ordering is fantastic for reading data. We've solved that problem, right? Well, not quite. We've created a brand new headache for ourselves. What happens when you need to change something? If your data is all perfectly sorted and you need to squeeze a new record into the middle, you have to physically shift everything that comes after it. That's a huge, clunky, and incredibly slow operation. We've just traded one problem for another. So how do we solve this new writing problem? The answer is our second pillar, and it's a wonderfully counterintuitive idea: immutability. As the subtitle says, it's the art of not changing things. The solution to changing data is to just stop changing data. Here's how it works. Let's say you want to update a record. Instead of finding the old data and overwriting it, we just ignore it. We take the new, updated version and simply write it to a brand new spot, usually at the end of the file. Then, the last step is to just update a little pointer or an index to say, hey, the latest version is over here now. The old version, it's still there, completely untouched. Now, this is where you realize how brilliant this simple rule is. All those messy, complicated problems you get when, say, two people try to edit the same thing at the same time, a lot of them just disappear. And as a huge bonus, since we never actually delete the old versions, we get a full history of every change automatically. It's like a built-in time machine for your data, for free. Okay, our blueprint is looking really solid. We can read fast, we can write smart. But there's one final enemy we have to face, and it's not an algorithm, it's just the laws of physics. We have to deal with the hardware itself, and specifically a massive speed gap between different parts of our computer. We need a bridge. Here's the bottleneck, plain and simple. Physical storage, we're talking hard drives, even modern solid-state drives, is, in computing terms, unbelievably, painfully slow. And on the other hand, you have memory, or RAM, which is blazingly, ridiculously fast. The speed difference is enormous. It's like comparing the speed of a bicycle to a fighter jet. This gap is the final hurdle for our design. So the solution is our third and final pillar, buffering. We use that super fast memory as a temporary holding area. Instead of writing every single tiny change to the slow disk one by one, we collect a bunch of them in memory, in a buffer, and then write all of them to disk in one single, big, efficient batch. It's basically the same reason you use a shopping cart at the grocery store instead of carrying one item to your car at a time. And that's it. Those are the three pillars. So now let's zoom out and put all the pieces together to see the complete blueprint we've just designed. This is the foundation for pretty much every high-performance data system out there. So, to recap, first, we use ordering to give our data structure, which makes finding things super fast. Second, we handled changes with immutability, which cleverly avoids all the problems of modifying data in place. And finally, we use buffering to outsmart our slow hardware by batching up our writes in fast memory. So why does any of this matter to you? Because every single app on your phone, every website you use, is built on these principles, and they are constantly making silent trade-offs between them. Is an app designed for lightning-fast reads, like a search engine, or is it built to handle a constant fire hose of new data, like a social media feed? Now that you know the blueprint, you can start to see the invisible engineering choices everywhere. So next time you're scrolling your favorite app, just ask yourself,